Hello everyone. The title of our paper is Study on Low Power Sensor and Heater for PCR Microchip, and I'm from Dalian Polytechnic University. Our presentation is divided into 4 parts. The first part is the introduction. The second part is the development of sensor and heater. And the third part is the characteristic analysis. And the fourth part is the conclusions. Okay, let's go to the first part of our presentation, the introduction. PCR is an enzymatic synthesis reaction dependent on DNA polymerase in the presence of polymerase primers and 4 deoxyribonucleotides. It works through 3 steps: high temperature denaturation of double stranded DNA, low temperature annealing of primers and templates, and primer extension and suitable temperature conditions. Through repeated cycles of these 3 steps, PCR can achieve exponential amplification of specific DNA sequence yield with the number of cycles, thus achieving the goal of rapid and large-scale amplification of template DNA. PCR biochip is an integrated PCR microreactor which is made on silicon glass and organic polymer by using the technology of microelectromechanical system. It can control the temperature of a reaction zone actually by using heater and temperature sensors integrated on the chip. It fully embodies the advantage of microchips such as high efficiency, rapidity, and saving regions. In this paper, the characteristics of a self-developed low-power temperature sensor and low-power heater for integrated PCR chip are analyzed. Now let's go to part 2, development of low-power temperature sensor and heater. There are 2 main types of PCR microchip fabricated by MEMS technology. The first is the single reaction zone structure, in which the whole process of amplification is carried out in one reaction chamber, and the continuous cycle of PCR amplification is realized by periodically changing the temperature in the reaction cell. The second is the 3 reaction zone structure. We have developed a single reaction region integrated PCR chip. The next part is the material selection of low-power temperature sensor and heater. Based on the literature, it is found that chromium and nickel chromium alloys are good heating material, and nickel is a good temperature sensor material. In this paper, we hope to use the same material to make temperature sensor and heater, because the reduction of process means the increase of chip yield. Therefore, chromium and nickel chromium alloy and nickel are used to make heaters and temperature sensors respectively. Next, we will give the design of low-power temperature sensor and heater. 4 independent PCR reaction chambers are etched on a single crystal silicon of type N. In order to improve heating efficiency and ensure accurate temperature control, the area of low-power heater at the bottom of the reaction chamber should be enlarged as much as possible so that the reaction chamber can be heated uniformly. The low-power temperature sensor should be placed in the middle of the reaction chamber bottom. Figure 2 shows the structure of the low-power temperature sensor and heater designed in this paper. The longer resistance is the heater and the shorter resistance is the temperature sensor. The line width of the thin film resistance is 50 micrometer, and the distance between the lines is 100 micrometers, and the area of the welding pad at the top of the resistance is 200 multiplied 200 square micron. Next, we will give the fabrication of low-power temperature sensor and heater, which is combined with the fabrication of PCR chip. Based on a large number of references and previous work experience in the laboratory, wet etching and sputter process is adopted. The first step is, according to the design scheme, the required photolithographic masks are obtained by drawing graphics on coordinate paper, carving red film, exposure, development, and stereotyping. The second step is the silicon dioxide thin film with thickness of about 1 micrometer are grown on both sides of single crystal silicon by thermal oxidation method. The third step is on the side without silicon nitride film. The window of PCR reaction chamber is engraved on silicon using photolithographic mask. And the fourth step is, because of the incompatibility between silicon and PCR, a thin silicon film is grown on the inner wall of the reaction chamber by thermal oxidation. And the fifth step is at the bottom of the reaction chamber. A thin film heater and a thin film temperature sensor are fabricated. The sixth step is pressure solder joint, and the seventh step is the alloy film is bonded by hot pressing with the gold wire ball welding machine to connect the external lid. Okay, now let's go to the third part of our presentation, the characteristic analysis of low power temperature sensor and heater. According to the temperature requirement of PCR amplification reaction, the analysis range of heater and temperature sensor is chosen in the range of 30 to 110 degrees centigrade. Figure 3 and Figure 4 show the temperature characteristic curves of two chromium film resistances. It can be seen that the chromium film resistance has no linear temperature characteristic and is sensitive to the temperature. Figure 5 and Figure 6 show the temperature characteristic curves of two nickel thin film resistances. It can be seen that the resistance of nickel film has good linear temperature characteristics in the temperature range of 30 to 110 degrees centigrade and is very sensitive to temperature. The variation of resistor is tens of ohms for every 10-degree change of temperature. This shows that the resistance of nickel film is a good temperature sensor. but it is too sensitive to temperature, therefore it cannot be used as a filter. The temperature characteristic curve of nickel chromium alloy film resistance is no longer given here, as its resistance value is hardly varies with temperature. So this shows the nickel chromium alloy is a good heating material, but it cannot be used to make temperature sensor. In order to verify whether the nickel chromium alloy thin film resistance heater can meet the needs of PCR amplification reaction, the heating effect of its PCR chip is tested by microthermocouple. Figure 7 shows the heating characteristic of integrated nickel-chromium resistance. The resistance value tested is 1281 ohms. The abscissa is the applied voltage and the ordinate is the highest temperature that can be reached in the reaction chamber of PCR. It can be seen from the figure that the heating effect is very poor when the applied voltage is low. However, when the applied voltage exceeds a certain crucial value, the heating effect varies greatly, and the maximum temperature in the reaction chamber increases approximately linearly with the increase of the applied voltage. Next, we will give the analysis of heating characteristic. The amplification reaction of PCR is repeated in 3 temperature zones, so the heating speed in a single reaction zone PCR chip is very high and generally requires heating speed not less than 0.5 degrees centigrade per second. In order to verify whether the resistance of nickel chromium alloy thin film can meet the requirement of heating rate of PCR amplification reaction, the heating states of 2 thin film resistors are tested. Figure 8 and Figure 9 show temperature-timed characteristic curves of thin film resistors with resistance values of 1281 ohms and 504 ohms respectively. It can be seen from Figure 8 and Figure 9 that the temperature rises rapidly in the first 30 seconds, and after the 30 seconds, the temperature rises slowly. After 90 seconds, the temperature changes more slowly and gradually tends to a constant value. Based on the above analysis, the nickel chromium alloy film resistance heater can meet the needs of the temperature change of the PCR amplification reaction and can be used as the heater of the PCR microchip. In order to test the temperature uniformity in the reaction chamber, the temperature is measured by sticking our microthermocouples to the bottom of the reaction chamber. The temperature time characteristics of 4 test points are shown in Figure 10. It can be seen that the temperature uniformity in the reaction chamber is very good, and the temperature of each point is comparatively consistent. This shows that the heater designed in this paper is reasonable and can meet the requirement of the temperature uniformity for PCR amplification reaction. Okay, now let's go to the last part of our presentation, the conclusions. A single reaction zone integrated PCR chip is designed and fabricated. The low-power temperature sensor and heater are made of chromium, nickel, chromium alloy, and nickel respectively, and are integrated at the bottom of the PCR reaction chamber. The results show that the nickel-chromium alloy film resistance produced in this paper can meet the requirements of heating speed and temperature consistency of PCR reaction chamber, and can be used as heater of PCR microchip. The results shows nickel film resistance can be used as temperature sensor of PCR microchip. This is the end of our presentation. Thank you for listening.